Hey everyone, and welcome back. So today we're going to dive into a really classic coding puzzle. How do you fix a binary search tree when just two of its nodes have been messed with and swapped? This one looks pretty simple on the surface, but trust me, the solution is super elegant. It's a really great way to test how well you really know your data structures. All right, but before we even touch any code, let's have some fun with this. I want you to imagine we're detectives rolling up to a crime scene. We've got this system, this tree that's supposed to be in perfect logical order, but it's been tampered with. Two elements are out of place, and it's our job to find them and restore balance to the system. So first, every good detective needs to know what the scene is supposed to look like, right? This is Exhibit A, a perfect, healthy, binary search tree. And the golden rule here, the one rule that holds everything together, is super simple. For any given node, everything to its left must be smaller, and everything to its right must be larger. That order is absolutely key. And this is our crime scene. Now, look, at first glance, it kind of looks okay, right? It's a binary tree, but it's broken. The structure is fine, but the values inside are all jumbled up, breaking that fundamental rule we just talked about. We know for a fact that exactly two nodes were swapped, and that one tiny change has completely wrecked the tree's internal logic. So take a quick look. Can you see them? Can you spot the two nodes that are in the wrong spot? Yeah, maybe in a small tree like this, you might get lucky. But what if this tree had thousands of nodes? You'd be looking forever. We need a system, a real method to crack this case. So let's get into it. All right, so no more guesswork. To solve this, we're going to lean on a fundamental principle, a golden rule that every single valid binary search tree has to follow. This rule is going to be our guide to finding the culprits. And that golden rule? It's called the in-order traversal. It's just a specific way of walking through the tree. You go all the way left, visit the node you're at, and then go all the way right. And here's the magic trick. If you do an in-order traversal on a healthy, correct binary search tree, you will always get a list of its values in perfect ascending order, every single time. This is like a law of physics for BSTs, and it's the law our culprit broke. Okay, let's see this in action on a tree that's actually working correctly. We go all the way down the left, we visit that node, then we pop up to its parent, visit that, and then we go explore the right side. And what do we get? A perfectly sorted list. See? This is the principle we're going to use to find the error in our broken tree. Okay, investigation time. We've got our forensic tool, the in-order traversal. Let's run it on our crime scene tree and just watch. We're looking for that one moment where the sorted order just snaps. All right, here we go. We start our traversal. We go all the way left. We find the node with 1. Okay, first in our list. Then we come back up to its parent, 3. So our sequence is now 1, then 3. So far, so good, right? 1 is less than 3. The rule is holding up. For now. Okay, from the 3, we're supposed to go right. And what do we find? The node with 2. So now our sequence is 1, 3, 2. And wait a minute, violation. 3 is not less than 2. The alarm bells are ringing. We just found our first piece of evidence. The law has been broken. So this right here, this is the trigger for our investigation. The second you see a previous value that's bigger than the current value, boom, you've got a clue. And what's really important here is that the previous node in this first violation, that's always our first culprit. Always. Okay, we've found the break in the pattern. Now let's use that clue to nail down exactly which two nodes got swapped. You know, the logic here is actually really slick. So when we hit that first violation, where the previous node is bigger than the current one, that previous node, in our case the 3, is definitely one of our culprits. We'll call it suspect number 1. Now, the current node, the 2, becomes our temporary suspect number 2. We keep going just in case there's another violation down the line, because if there is, the current node of that violation would be our real second culprit. All right, so let's recap the investigation. That first violation immediately told us our first culprit was the node with the value 3. And as we continue the traversal through the rest of the tree, guess what? No more violations. Everything else is in order. So that confirms it. Our temporary suspect, the node with the value 2, is indeed our second culprit. We've got him. The swapped nodes are 3 and 2. Okay, we've identified the perps. Now for the easy part, fixing the tree. And you'll be surprised how simple this is. We don't have to rebuild anything. It's just one final move. It's this simple. We just swap their values back. The node that had the 3 now gets the 2, and the node that had the 2 now gets the 3. That's it. We don't touch the structure, we don't move pointers around, we just fix the data. And how do we know we got it right? Well, let's run our test again. We do an in-order traversal on our newly fixed tree, and what do we get? 1, 2, 3, 4. A perfect sorted sequence. The golden rule is restored. Case closed. So what's the big takeaway here? Think about it. We could have tried a brute force method swapping every possible pair of nodes. That would have been a nightmare. Instead, we just trusted the fundamental rules of the data structure itself. By understanding why a BST works, we found this incredibly clean and efficient solution. And that's pretty much the whole story. But I do have one last question for you to chew on. In our example, the two swapped numbers, 3 and 2, ended up right next to each other in that broken sequence. That gave us just one violation. But what if the swapped nodes were far apart? Like, what if the 1 and the 4 were the ones that got swapped? How would our logic handle that? How many violations would you find then? And how would that help you identify the second culprit? Something to think about.